Good morning. 8th of April 2024 is lovely Monday morning. Let's get started on problem 4b. These two functions, I didn't really know about them, so I went back to look at the problem 18d of section 3, and it was kind of abstract. So you see this guy to the third is a cusp form because it's delta z times delta of 2z. So everything works out without much detail in problem 18d. So I needed to get a little more acquainted with the functions. And the first thing I did was to find the series expansion by the definition, and then the first 20 terms. They turn out to be multiplicative. And then G, where we just take the first 10 here, copy them, and then double the exponent. And then that's what we get. And then I realized that if we added this guy, you can see we have q squared here, and that's minus 8. We have 8q to the fourth, that's plus 26. So if you add f and 8 times g, then we end up with odd exponents, meaning that it's an eigenfunction of t2 with eigenvalue 0. We had that in problem 2. So that was nice. Next, I wanted to check out what were the order of the zeros. We know that eta has no zeros in H, so the only zeros are at the cusps. And the zero at infinity, that follows from the series expansion. It has order 1, and of course G has order 2. And then the zero of naught, I actually computed that explicitly, computing f operating with s, and found out that powers of, or the first term was q1/2, and all of them, and then they were all integers times q. I don't know. Yeah, they were all multiply of q1/2. But naught has ramification index 4, so that means that the zero at naught has order 2. You see the sum of the zeros may give 4, or the sum of the order of the zeros gives 4. So that means then we know 1 is 2, then the other ones are 1. So I didn't have to compute 1/2, the expansion at 1/2 explicitly, which was nice. So now I feel I know something about these functions. Then we should prove that when n is odd, Tn acts by multiplication. And we did that in problem 2. So my first idea was to copy what we did in problem 2, maybe with alpha 2 instead of alpha 4 as in problem 2. But the next idea was to use this, because we prove it for odd n, and here m is 2. So what does it say here? N being prime to 2, that means that n is odd. So it should be a simple application of problem of part A. So let's see if I can do that. I see this tends to vanish. The picture of me will probably vanish again. I haven't found the reason by it, but let's see if I can finish problem B fast. Now, assume, gone again. Tn, of course, n is odd, of f is lambda n f. Then Tn mark of G is Tn of f of 2z. Oh, we have to put z on then. Or I could write composed with 2, but let's not do that today. And Tn of f, that was lambda n f of 2z equals lambda n of f of 2z, which is g of z. So they have the same eigenvalues. Which is exactly what we should prove. And then we shall find the matrix T2. But I've already started on that, so let's finish that while we are at it. We have T2 of f plus 8g equals naught. So we just need to find out T2 of f. Or g, whichever is more easy. You know what? T2 of g, that's just equal to f. And that means T2 of f plus 8 T2 of g equals naught. T2 of f equals minus 8 T2 of g equals minus 8f. So the basis is f point g. And f maps to minus 8f plus naught times g. And T2 of g equals f. So that's the matrix. And now for all of the Tn, I'm spent at this moment, so let's stop. Oh, I misread problem C. That explains why I wasn't really able to do it. A basis of all the normalized eigenfunctions for all Tn. So we know any basis will be used when n is odd. So we're only liking n equals 2, because then T2 and Tn with some odd commute, so we can use the same basis. This doesn't make sense. There's something wrong here. I don't quite understand it. But this had eigenvalue 1, so we can use actually we need to solve this problem. Now T2 of G vanishes. T2 of this vanishes. T2 of F equals 8. T2 of minus. Now what's up here? Oh, that was T2. So if we take this one and then half all the powers here, and I believe that's what T2 does. That gives F, right. So that was this formula. Now if we applied here T2 of F, equal plus 8 T2 of G, you see, my problem is that this says that under T2, what? F goes to minus 8F, and G goes to G, which it doesn't, it goes to F. So there's something wrong here. Let's assume this is right. T2 of F plus 8G vanishes. T2F plus 8T2G vanishes. That means that T2 of G is F. That is T2 of F is minus 8, yeah. But G vanishes. No, G doesn't vanish. G gives F. So it should be 1 naught. but that doesn't make sense, because then G maps to F, and F maps to minus 8F, so it feels wrong. But on the other hand, it leads to that we can use like F and F plus 8G as a basis for all Tn. Say the basis of normalized. Oh, they are not particularly normalized, are they? F, that's normalized, and F plus 8G, that's normalized as well. Lovely. So they are normalized, meaning that A1 equals unity. So that's the basis. And in that basis, the matrix becomes minus 8, 0, 0, 0 for T2. So we didn't have to find the eigenvalues for all the Tn's. That was what stopped me dead in my tracks before. I believe this solves problem 4. While editing the video, it occurred to me that this was presumptuous. I might have had a good reason for doing it, but I didn't understand it while watching while editing the video. So I thought, let's do it properly here and assume that we have an eigenvalue alpha f plus beta gamma, and then expand Tn mark on f and g. It's linear, of course, and then on f it's Tn of f, and on g it's Tn of f taken of double argument. Tn of f, that's, oh, it could just be Tn mark of f. That's given by this guy. And so is Tn of f. We expand, and f with double argument is g, and then we get b squared times f times g itself by double z. And my point here is that this guy doesn't lie in S8 gamma naught 4. So how can we see that? That was g of 2 z, meaning it starts with q to the 4th. And no linear combination of this can cancel q and q squared. Therefore, b squared must vanish, and that means b vanishes. And therefore, an eigenfunction must have b equal to 0. And that means that since it's not a zero function, or must it, where did the lambda come in? I forgot the lambda. I'll just put that n, Tn of f here we miss the lambda, and here we miss the lambda. So there's a lambda before all of these. And now we can conclude that either B vanishes or the eigenvalue vanishes. And then my argument carries through.